Here's a scenario that requires you to put it all together. Kinetic friction, static friction, dynamics, and kinematics. I'll have a series of problems for you to solve, so get a calculator ready. Young Calvin and his best friend Hobbes are going sledding. The mass of Calvin and his toboggan here together is 30 kilograms, and we can look up the coefficients of static friction and kinetic friction for wood on snow, so wood toboggan here, in standard tables. So there we see wood on snow, and we've got our values. What I would first like you to compute are these three things. The weight of Calvin and his toboggan, the maximum force of static friction that the snow will be exerting on the sled, and the magnitude of the force of kinetic friction that the snow will be exerting on the sled once the sled is in motion. They're going to be moving over horizontal ground the whole time, and they are starting from rest. So pause the video, compute those three things. Got it? First, the weight. Weight, of course, means the force of gravity. So m times g to find a weight of about 300 newtons. The maximum force of static friction, that's mu s times the normal force. The normal force would be equal to the weight, since they're on horizontal ground and those forces will be balancing each other. So mu s times the normal force, about 36 newtons. And the force of kinetic friction on the sled once it's moving, mu k times the normal force, so about 18 newtons. All right, we've got those three values. Now, here's the scenario. This graph is depicting what's about to happen. Okay, so I'm plotting force versus time. Calvin's going to hop on the sled, and Hobbes over here is going to start pushing them. In red, I've got the force applied by Hobbes to Calvin over time. And in light blue and orange here, I've got the force of friction that the snow is exerting on the sled versus time. So we see a scale here for the force in newtons and for the time in seconds. And I've divided up this story into 5 time periods. So I would like you to first interpret what's going on in this scenario here. So for each of these time periods, 1, 2, 3, 4, and 5, can you look at this graph and interpret what is happening? How is Hobbes pushing? How is Calvin moving? If he's moving, when does he start? When does he stop? Can you sort of tell the tale of what's going on based on the graph? Interpret the graph for us. Pause the video now and come up with a story for each of these 5 stages. Ready? Okay, here's my interpretation. During this time period, Hobbes starts to push. His force starts at 0, and he pushes harder and harder and harder, up to 24 newtons. But that whole time, the force of static friction is growing to match him, so Calvin doesn't start moving, and Hobbes gives up at this point and stops pushing. Calvin is still at rest. Static friction was not overcome. Hobbes takes a breather for a couple of seconds here, exerting no force, and then tries to push again. This time he pushes even harder. His applied force grows and grows and grows up until this moment when static friction, which has been growing to match him the whole time, can no longer match that applied force. Once Hobbes pushes with a little more than 36 newtons of force, that's the maximum force of static friction, he breaks static friction right there. And at this moment, Calvin starts to move. So from that moment onward, Hobbes lets up a little bit, doesn't have to push quite so hard anymore, and he continues to push at a constant 30 newtons of force for this whole time period, while kinetic friction is opposing him. So during this time, Calvin is accelerating. The applied force by Hobbes is greater than the opposing force of kinetic friction, so Calvin is speeding up during this whole time period 4. And then at this moment, we see Hobbes' applied force suddenly drops to 0. That's because Hobbes falls flat on his face in the snow, exhausted, and lets go of Calvin, who continues to slide onward. Kinetic friction doesn't disappear because Calvin is still moving, but the applied force is gone. So from this moment onward, Calvin is going to be slowing down as friction brings him to rest. That's the tale. Next, I would like you to apply dynamics to this scenario. Starting with free body diagram and aligning your axes with the acceleration, use those steps to draw free body diagrams for Calvin and the sled at these three times. At the end of period 3, so at this moment just before we break static friction, and then throughout time period 4, and then throughout time period 5. Draw an FBD for each of those. Pause the video. Ready? Okay, here are the FBDs. Right at the end of section 3, we've got the normal force and gravity balancing each other in the y direction. Oh, here's my AAA step right here. Picking my axes, regular XY axes will do just fine for all these times. And then here's Hobbes' applied force being matched by the maximum force of static friction. So we're in static equilibrium just before we break static friction here. Hobbes only has to push a little bit harder, then we break static friction and start to skid. Then throughout section 4, the applied force here is a little less than the 36 newtons here. Here it's 30 newtons, but our friction has dropped down to the value for kinetic friction. So here, Calvin is accelerating, speeding up with an applied force that's beating out kinetic friction. Then, after Hobbes drops into the snow and Calvin continues to slide onward, the applied force is gone, and we've just got kinetic friction slowing him down. Okay, got your FBDs. Now, I would like you to find Calvin's acceleration during period 4 and then during period 5. Use your free body diagram and use what you know of dynamics to compute his acceleration during those 2 time periods. Pause the video. Ready? All right, so we're going to use Newton's second law. That's exactly what Newton's second law is for, finding acceleration. We've got to find their net force in the x direction. We know everything's balanced in the y direction, so nothing to worry about there. Net force means sum up all the forces in that direction. So, during period 4, while Calvin is speeding up, we've got Hobbes' applied force being opposed by that force of kinetic friction. There's our 30 minus 18 newtons over the mass of Calvin to find 0.4 meters per second squared. That's Calvin's acceleration during this period as he's speeding up. Then once Hobbes drops and Calvin starts to slow down during period 5, the only force in the x direction is that force of friction in the negative x direction, slowing him down. So negative 18 newtons over the mass, so minus 0.6 meters per second squared. That's Calvin's acceleration during this time as he's slowing down. Last set of tasks involves kinematics. Use your knowledge of kinematics to compute Calvin's maximum speed and determine how far Calvin slides from the moment Hobbes releases him until Calvin eventually comes to rest once again. Pause the video. Ready? Good old kinematics. You can pull out your guess strategy, and as Calvin hits his max speed, when does that happen? Well, Calvin's at rest this whole time. Then here he starts to move. He's accelerating this whole time, speeding up, so he must hit his max speed right here just as Hobbes releases. So max speed is right there. So find his speed at the end of this period when his acceleration is 0.4 meters per second squared that whole time. We can use this constant acceleration equation right here. Starts from rest, hits his max speed at the end. It's a 20-second time interval from there to there, during which he has that acceleration, so he hits about 8 meters per second at the end. And you know that's about 16 or a little more than 16 miles per hour, moving pretty well. Then, how far does he slide? Oh, by the way, there's other ways to solve this. You could use other kinematics equations. Here's just one example. Did you use a different kinematics equation? Different constant acceleration equation? Fine if you did. You should be able to get that same result. Now, how far does Calvin slide? From this moment here when he's released until he eventually comes to rest, I chose this constant acceleration equation. I'm going to rearrange it to solve for the distance that he travels, delta x. I know his final velocity will be 0 when he comes to rest, and his initial velocity is that v max. So final minus initial, 0 minus v max squared, then divide by 2 times his acceleration. So that's minus the 8 meters per second squared over 2 times his acceleration during this period when he's slowing down, which is the negative 0.6 meters per second squared. Comes out to about 53 meters right there. A new personal record.